Okay, so just like we had an alternate way of calculating for current, there's also an additional alternate way of calculating voltage or potential difference. Okay, so if you recall from Ohm's law, V is equal to current times resistance. Okay, the alternate way that we can calculate for potential difference is by doing energy over charge. Okay, or you can think of this as the energy that's in the electrons divided by the number of electrons that we are referring to. So if we wanted to look at, let's say, the voltage of a light bulb, remember we would connect a voltmeter. The voltmeter is measuring the energy at two different points. And of course, you have to take into consideration how many electrons are actually passing through that point with that certain amount of energy. So the units are the same for V and Q that we've already seen. So we have voltage and coulombs. Energy is in units of joules. Okay, so the symbol for that, so this is the full word, but the symbol for it for the unit is a capital letter J. Okay, so 1 volt is equivalent to 1 joule per 1 coulomb. Okay, so it's the amount of work that is required to move 1 coulomb of charge between 2 points on the circuit. Okay, so essentially a volt is equivalent to joules over coulombs, or energy over charge. So again, another 3 variable formula. So what I suggest you do, so normally in class, if we were doing a test in class, I would provide you with this formula. I would suggest that you have with you maybe a formula sheet. So something that's beside you that you have reference to for the different formulas, because normally I would give this to you on an in-person test anyways. You should be able to convert the different variables. So if you had to isolate for E or Q, you should be comfortable with that at this point in time. So if we wanted to isolate for E, right, you do the opposite function of whatever it's with. So we're going to do times Q, whatever you do to one side, you do to the other. So E would be basically Q times V. Or, let me just rewrite that again. If we had to isolate for Q, again, you do the opposite function. So you divide by V on both sides. So Q would be equal to E over V. Okay, so again, another 3 variable problem. So let's start taking a look at some examples. So once you kind of learn how to do one, right, they all become kind of very familiar. So again, we're going to be using grasp. We're doing a word problem here, right? So what is the potential difference across an air conditioner if 72 coulombs of charge transfers 8.5 times 10 to the 3 joules of energy? So remember, we did look at scientific notation numbers way back when at the beginning of this course. So you should be able to put this into your calculator to actually do the calculations, okay? So let's get going with what we want. So we're looking for voltage. We have the charge, right, 72 coulombs, and we have energy, and everything is in the proper units. Okay, so V is equal to, let's go back to the original, E over Q, right? Okay, so when we plug in our value, just a reminder, you don't have to write this in, I'm just doing this to remind you. Whenever you put scientific notation numbers into your calculator, you want to make sure that you put them in brackets. That way your calculator recognizes that this is one value, okay, divided by 72. So we have bracket 8.5 times 10 to the 3, close bracket, divided by 72. So we have 118.056, but remember we're going to round that, and the unit is volts. So both of our numbers from our original question have 2 significant digits. So this would be 120 volts once we round that to 2 sig figs. Okay, so then we can say the potential difference of the air conditioner is 120 volts. Okay, so give this one a try, pause the video, and remember to use grasp and see how you do. Okay, so let's get going here. So we have, it requires 0.600 kilojoules of energy to transfer a quantity of charges between points X and Y in a circuit. So we have the energy, right? So just like with any other instance where you have kilo, so kilojoule or kilovolt or kiloammeter, whatever the case is, the unit conversion is always the same. So to go from kilojoule to joule, you would multiply by 1,000, right, to get 600 joules. We're also told the potential difference was measured to be 30.0 volts. How much charge was transferred? Okay, so we have to rearrange. So Q is equal to E over V. So we have those values in the correct units, so we're just going to plug that in. So we have 600 divided by 30, which gives us 20 coulombs. Okay, now we actually need more significant digits than what the number 20 is giving us. So 0.600 is 3, and so is 30.0. So we need to make this one significant digit into 3. So hopefully you realize you'd have to put a decimal and an additional 0 there. So remember that decimal makes these trailing zeros count, and we needed to add one more so that way we had 3 digits in total. And then you would, of course, have a therefore statement here. So the amount of charge that was transferred was 20.0 coulombs. Okay, now the last part of this is actually nothing new, okay, but you're going to start seeing multi-step problems, okay? So here are the two formulas that we just finished learning about. So we learned about an alternate way to calculate for voltage with energy and charge. And we also learned an alternate way to solve for current, which is charge over time. Now, what this is doing here is basically combining these two into one formula. So if you were to rearrange this, which we actually already did before, E is equal to V times Q. If you were to rearrange Q, Q is equal to current times time. So what happens here is instead of this Q, they're plugging in what Q is equal to from the other formula. So E can also be equal to voltage times current times time, okay? You do not have to use this formula. You can actually keep them as two separate formulas. I'll show you what I mean once we start getting into examples. But the point is you're going to have to do more than one step now. So there are going to be problems you're going to see quite often that you're not using just one formula, where you're going to be using multiple formulas. Okay, but keep in mind, you only deal with significant digits at the very, very end. So if you have to continue and you have more steps to do, you do not round at the beginning. You round it only at the very, very end. Okay, so I'm going to show you one and then you're going to try one out. Okay, so calculate the energy stored in a 5.6 volt battery. We want energy that can create a current of, so we have current of 4 milliamps. You know what, right away, let's convert this. So to go to amps, we're going to divide by 1,000. So it's going to be 0.004 amps. And we have time in minutes. So we know that we're never dealing with minutes. We're going to have to deal with seconds. Oops. Pardon me, minutes have to go on the bottom. 1 minute is 60 seconds. So 5.1 times 60 is 306 seconds. Okay, so here's all the information that we have. We're looking for E. Okay, so here are the formulas that we currently know. Let's go back to the original formulas. We know E is equal to Q times V, right? That's the formula that has E in it. So let's write that down. So we have V, no problem. V is given, but they do not give us information about charge. So this is what I'm talking about. So before we can solve for E, you would have to first solve for Q, which we know Q, we have to use the other one. Pardon me. Q is equal to time times current. Okay, so Q is equal to time times current. Now you're probably wondering, well, why am I not using this Q to solve for it? Because we don't know E. If you have two items that are missing, so we don't know E and we don't know Q, you have to use an alternate way of solving for one of the things you are missing. So because we have time and we have current, we can solve for Q here and then plug it in to solve for E. So that's exactly what we're going to do. So we're going to plug those in right now. So Q is equal to 306 seconds times 0.004 amps. So we have 306 times 0.004, which gives us 1.224 coulombs. Okay, do not round this. We're not done. We're going to now take this number and we're going to plug it into the Q up here because now we know this information. So now we can solve for E. So see how this is like a multi-step problem. So E is equal to Q, which we now know, times voltage, which is given in the question. So we have 1.224 times 5.6. So this gives us a value of 6.8544 joules. And this is our final answer. So now we're going to look at sig fig. So we have 2, 1, and 2. So we have to round this to only 1 sig fig, which is 7 joules. Okay, and then of course we would need a therefore statement. So the energy stored is 7 joules. Okay, so multi-step problem. So actually we didn't learn anything new here. We're just taking the two other formulas we learned and now doing a two-step problem with them. Okay, so try this one out, pause the video, and then this will be the last one for today's lesson. Okay, so how much time, so we're looking for time, is required to transfer 25 joules of energy from a 3.2 volt electrical source that produces an electron flow of 2.0 amps. Okay, so we have here, we're looking for time, we have energy, we have voltage, we have current. So let's go back to our original question. So time is equal to Q over I. Okay, so let's write that down. So time is equal to Q over I. So we have I, but we're still missing Q. So that means we have to solve for Q using the information we have. So if you recall, Q is equal to E over V. And we can use that because we have energy and we have voltage. You have to kind of look to see what information do you have to work with. Then we're going to plug in for Q and solve for time. Okay, so let's do it.